So there are four fundamental different ways to find Norton and Thevenin transforms. Here's the first. This is the easiest method, and it should be the first method that you attempt, but it won't work with dependent sources. Since a Norton or a Thevenin is just a single source combined with a single resistor, if you've got a circuit that you can simplify through successive transforms, that's the method you should use. So for instance, for this circuit, you want to find the Thevenin equivalent transform of the circuit. The Thevenin is the one that looks like a single voltage source in series with a single resistor. So for this circuit, you would start off by doing a source transform to the left of those two circles. So in other words, we've isolated this section, we've put it in a black box, and we want to find the equivalent circuit using a source transform. And that's a current source in series with a resistor, where this is the same resistor value, and if this is a voltage source, this would be a current source by Ohm's law, V over R. And the rest is the same. And then we'd notice that these two resistors are in parallel. The voltage across them has to be the same. So you'd work out their equivalent parallel resistance, and you'd get a value for that. And now you do one last source transform, in which you'd multiply the resistor value here with this equivalent current source, and you would get this, and you'd recognize that that is the Thevenin equivalent, and you would stop. So that's the easiest way, but it will not work with dependent sources. The second method is almost as easy as the first. Use it if all of your sources are independent. To do this, you're going to first find the open circuit voltage using nodal or mesh methods, and then you'll find the equivalent resistance by zeroing all your sources. And to zero sources, what we mean is that if you've got a 0 volt voltage source, that becomes just a short, and a 0 amp current source just becomes an open. As an example, say you've got this much more complicated circuit, and it's not clear how you'd simplify that using the first method. To solve for the equivalent Thevenin resistance, find the output voltage, open circuit. Do that using nodal or mesh methods, just like you did for in other circuits 1's problems. Then, zero all the sources to find the REQ. So since zeroing sources means to make your current sources opens and your voltage sources shorts, you'll get a circuit that looks like this. To determine what resistors are in series or parallel, it's easiest to visualize if we push current into the top and extract it from the bottom, and ask what pathways can it flow through. And I see those three pathways. And that should start to tell us what resistors are in series or parallel. So for instance, I can see that these three resistors, all the current that goes to this first resistor has to go through the second resistor, has to go through the third resistor, so therefore those three resistors are in series. And so we can simplify the circuit. This top resistor is equal to this first resistor, second resistor, and third resistor. And so now it comes back together as here and here. That still looks kind of confusing, but I think we can simplify it once more. Watch how these resistors look if I draw it slightly differently. I'm just going to take this middle line and split it into two different lines. I think it's pretty clear that I haven't changed the nodes that any of these resistors are drawn on. All I've done is split this line into two lines. And now it should be clear that these two resistors up here are in parallel. And they're in parallel because they're combined at the top and the bottom. So these guys are in parallel. These are also in parallel. It's a resistor in parallel with a short. And so their combination for resistor in parallel with short is just a short. So now we can draw this more simply. If we call this R1, R2, and R3, we can draw it more simply as just R1 in parallel with R2, and then R3 goes away because it's been shorted out. And that is our REQ. And so now we've drawn both. We've determined both our REQ and our VOC, and now we can draw our Thevenin equivalent. It's just our VOC in series with our REQ. And again, we found our VOC just by using nodal or mesh methods. And we found our REQ by zeroing our sources and just by collapsing the resistors in series or in parallel. There is a third method that you can use if your circuit has a dependent source or multiple dependent sources, but it must have at least one independent source to kick those dependent sources into action. I'm going to draw your circuit now as a black box with these two terminals. And your first step in using this method is to find V open circuit, just like you did in method 2, using nodal or mesh methods. Then, after you find V open circuit, I'll record it over here. After you find V open circuit, you'll next short the output terminals. And you'll measure some sort of I short circuit that flows. And when you determine that, the Thevenin equivalent will be a voltage source, a VOC, with an REQ that's equal to, by Ohm's law, of VOC over I short circuit. You could instead determine the Norton equivalent directly by saying it's the I short circuit, again with the same REQ as you evaluated above. The nice thing about this method is that it works not only theoretically to solve circuits, but it works in the field. If you had a complex circuit that you couldn't open up on the inside and determine what it was made of, you could actually take a digital ohm meter, a digital voltmeter, and measure the VOC just by connecting the terminals here. And you could short the output and then measure the short circuit current that flowed. And from that you could construct the actual Norton or Thevenin equivalent. The last method we'll discuss is the most complex of them all. You'll only use this method if you have no independent sources in your circuit at all. They're all dependent. If all your sources are dependent sources with no independent sources, there is nothing at all to kick that circuit into action. In other words, 0 volts is a perfectly valid solution for this, no matter how complicated you make your circuit. Because if everything is 0 volts and 0 amps, there's nothing to make these sources do anything different. So the Thevenin equivalent of that complex thing will always look like a single resistor. The only question is, what will that resistor be? The way you determine it is to attach a test 1 volt source to the output. Determine the current that flows into your circuit, call it I test, since we've applied a V test of 1 volt. Determine what current flows into the terminals. And then your single resistor that models everything to the left of those terminals is just V test over I test. So everything in that complicated circuit with all the dependent sources and resistors is just that one resistor, V test over I test. Now this circuit uses a 1 volt test source, but you could instead just as well apply a 1 amp test current to your input and then measure the voltage that it causes. So here your 1 amp would be your I test, you'd measure your V test, and then the formula for the equivalent resistance stays the same. I'll give more complete examples of each of these 4 methods in the next few videos, but first I want to review what source transforms and resistor simplifications are for the very first method.